As you're using the equations that you now know for straight line motion to solve various problems, we need to consider a detailed analysis of the position, velocity, and acceleration graphs as well. And we're going to start with analyzing position graphs. So let's do that. And what we're going to be interested in as we go through this is how do you get information about the other graphs given a particular kind of graph. If you have a velocity graph, how do you get a position and an acceleration? We'll start with positions, so we'll want to know how do we get a velocity and an acceleration graph from that. So let's begin. To start, when you analyze a graph, you need to ask yourself a couple questions. What kind of graph is this? And that may seem self-evident, but if you don't answer it correctly, you're in deep weeds. You're going to answer it with position, velocity, or acceleration. And then what information is given by, this is the second question, with a couple subparts. Reading the graph, the slope of the graph, and the area underneath the graph itself. What information is given by those particular operations or features. And if you ask those questions and answer them correctly, you will be on track. So, position time graph, we can call it x versus t. You know, that's just position. Or d versus t, displacement versus time. If x is always positive, you're only going in one direction, you never reverse direction, then it's displacement just as validly. So here's our x versus t graph. And just picking some random plot. Okay, so first of all, real simple. When we read the graph, what information do we get? This is not a trick question. When you read the graph, you get the information that's over here, which is position. When you ask for the information given by the slope, you recognize that, well, here's an example. Slope of a point is a tangent line to the graph, tangent to the graph at that point. And the slope of the line is y over x, or delta x over delta t. And you know what that is the definition of. That's right, it's velocity. Okay, last thing is area. Here's a segment of area given. Well, what does this correspond to? Here's an area. Well, to understand, you would go, area is, one dimension times another. So in this case, it'd be height times width. What are those dimensions? Well, the height is meters, and the width is seconds. So it's meters seconds. That's the unit for the area. So I'm sure you know what that is. So go ahead and just write it down in the blank here. Go ahead. I'm waiting. You're not so confident? Did you put velocity? Acceleration? Well, let's see. Velocity is meters per second, which is not meters second. Ooh, I know. Displacement. Oh, no, that's meters. Acceleration is meters per second per second. We still don't have meters second, do we? So, come on. That's simple. Meters times seconds. What is it? Are you tired of waiting? Well, good. I'll stop your anticipation and give you the answer. It's nothing. Ha ha. Tricked you. Actually, not. Just wanted you to process that for a while. You got to believe the units. A meter second sounds like it ought to be something simple and physically relatable, but I can't really tell you what that is. So it's nothing useful, at least. I should say, well, yeah, it is something. It's a meter second, but that's nothing useful. So you can just consider the area under a position graph of no use, position time graph of no use to us. There we go. Now, when you consider displacement, what are we talking about? Well, we're talking about x minus x0. So here's two positions on the graph, and I could call it x0 and x, or you can call it x1 and x2. That's comparable. Or x initial and x final, doesn't matter. But anyway, it's the difference between those positions. The instantaneous velocity, how do you get that from a position graph? We already did it. It's the slope of a point on the graph. That's the instantaneous velocity. Okay, just here showing that the displacement is given by the difference between those. So slope at a point, and then the acceleration. What information gives the acceleration on this graph? You'll notice that if it's a straight line, it's a uniform change in position, which means uniform velocity, because change in position is the dimensions of velocity. So if there's an acceleration, it means there's a non-uniform change in position. Therefore, the slope is going to change. And if the slope is changing, like here, it simply means it's curved. So if you see a curved section of a position graph, it denotes acceleration. If it's curved up, example right there, it means positive acceleration. If it's curved down, I call that curvy downy. Curvy uppy and curvy downy. And here is negative acceleration. That is a good example of negative acceleration, where the velocity gets less and less. Okay, so that's negative acceleration, curvy downy. Upside down bowl, positive acceleration, right side up bowl kind of thing. Now, how should you think about this graph to deduce information about the velocity? We're going to do that next, keeping in mind that what characteristic of this position graph gives you the velocity? We already covered that. It starts with an S and ends with OP, slope. So let's use that to our advantage and map out the velocity of the position graph. So we want to convert the position graph to a velocity graph. And we recognize that the slope of the position is the velocity. So we're focused on the slope. And we're now going to ask ourselves, what is the slope doing? First of all, is it positive? If it's positive, it's slanted up to the right. Or it's slanted down to the right if it's negative. Right? Okay. So once you answer that question, then more about the slope. What's the slope doing? Okay, it's positive or negative, but is the steepness changing? Okay, is it constant, which would mean uniform velocity? If the slope steepness isn't changing, the velocity is constant. In that case, there's basically three possibilities. It can look like this, that, up to the right, down to the right, or straight across. Now it could also be getting steeper. That would mean positive acceleration. It's curving upward like this. The speed is going up. If you just think about the slope at any point here, the slope lines get steeper. Or it's possible that it's getting less steep, in which case you have negative acceleration. So now an example of that would be like this. An upside down bowl, curvy downy. The speed is going down. The slope is getting smaller in magnitude. All right. Well, the rooster is telling us to wake up and analyze the rest of this now. So what can I conclude about the speed and the direction of the velocity from my answers to the questions? So here's our position time graph. Let's label each section to make sure we understand the nature of the motion of each section. First of all, we have positive velocity on the first part. And then that curvy part, it's curvy uppy, it's positive acceleration, plus A. The next part here is a straight line segment, at least it's supposed to be. So that's just positive velocity. And then we have another curvy part. If it's curvy, it's acceleration. If it's curvy downy, it's negative acceleration, which is what this is, an upside down bowl. And finally, we have negative velocity in the final segment. So let's go ahead and map this over to velocity. And what we recognize is the slope of the line is velocity. So it's a constant value here. So it maps over as a constant value of velocity, positive velocity. Notice the plot just got simpler. Instead of being a straight line, but instead of changing value, it's a constant value. Now in the next part, this curved region, that means the slope is increasing, and unless we have information that tells us otherwise, we assume that the slope is increasing uniformly along this curved region. Otherwise, it's too complex to visually analyze. So there it is, a uniformly increasing velocity, which is saying a uniformly increasing slope. It's kind of hard for me to show that, but if you put a straight edge along here and follow this, you'll see how that straight edge gets steeper and steeper. So this is positive acceleration, curvy, uppy. And then the velocity is going up as well. So in the next segment, we have a uniformly increasing position, which means a uniform velocity again. It's just at a higher value. It's a steeper slope. So that's positive V. Next section. Well, quite a bit's going on here. We have negative acceleration, velocity decreasing, and you might think about where the end point is going to be. The beginning point right here is going to be right where we are over here. What about the ending value? Well, keep in mind that at the beginning, at the middle, approximately here, the slope is what? What's the slope? That's right, it's 0. That means the velocity is 0 here. So at this point of the graph, it has to cross the 0 point on the velocity graph. So right here, we're here, and in the middle, we're all the way at the bottom here. I'm sorry, at the 0 point. And so it goes more negative, so it's swinging down like this, so the slope is getting less than 0. It's gone to 0 and it's gone below 0. So there it is. It drops all the way below 0 and into the negative because we have a negative slope. Now notice I don't know exactly how far to go. This is all conceptual. We don't have any scale and particular numbers here, but I could put them on the original graph, the position graph, and you could translate just as well. So this is negative acceleration. The velocity is going down. And in the final segment, it's a straight, uniform, well, it's a straight line, uniform slope of negative value. And there it is. There's the negative value of the velocity. This is the value of the slope along this interval. That's a good introduction to position time graphs and analyzing the various segments of that position graph and then translating them onto a velocity graph. In the next video, we'll do the same thing with a velocity graph and looking to see how it translates to acceleration. Stay tuned.